All right, so we're going to do a little more work in section 12.1 today. So more vector valued functions. There's only one thing that's better than vector valued functions, and that's more vector valued functions. Too much of a good thing? Well, we haven't even gotten close to too much. We barely touched them. So the first thing I want to do is look at an example. What we're going to talk about just for the first part here is kind of like we did with this homework problem. We want to, given a vector valued function, we want to sketch what the curve, the graph of the curve is going to look like. So let's work through one of these. We have, and since we looked at this other one, this one shouldn't be too hard. We have RT is 3 sine ti plus 4tj plus 5 cosine tk. So that's our vector valued function. We want to sketch the curve. So from what we talked about yesterday, we want to figure out some kind of relationship between the components and maybe write down the rectangular equations that relate some of the components. So how could we relate a couple of the components of this vector valued function? Anybody have an idea? We have some kind of circular thing going on between which components? X and z. So let's look at the x and z components. So we know that x equals 3 sine t and z equals 5 cosine t. And whenever I see a sine t and a cosine t, I always think of Pythagorean identities. So we know that sine squared t plus cosine squared t equals 1. We have this 3 and a 5. So how are we going to deal with that 3 and that 5? Divide. So we can say x squared over 9 plus z squared over 25 equals 1. So what does this give us? An ellipse. And we're thinking in 3 dimensions. What would be the surface if we were thinking of this as a surface? A cylinder, an elliptical cylinder. And our axis would be which axis? The y axis would be the axis of this elliptical cylinder. And then we have this linear thing going on with y. So what is that going to do? So in the xz plane, we have this, as t changes, we have our point moving along this ellipse, and we have a linear thing going on with the y component. So what's that going to make? So Griff did this.
Spiral.
So it's going to spiral. So it's going to move on this ellipse. If we project the movement onto the xz plane, it's going to be this ellipse. So it's going to go around this ellipse. And as t increases, it's going to go along the y-axis. So it's going to move around this ellipse. So we have this kind of a spring shape. So I'm just going to write down here. It's linear. I'm going to say linear in y. So if we were to try to sketch this, and it can get kind of tricky to sketch these. So here are my axes. I'll do my axes over here. minuses z, x, and y. So we have this ellipse. In the xz plane, I'm going to do the dotted lines down here. So my ellipse, I'm going to do the ellipse. It's going to move along this cylinder, which is along the y-axis. And as t increases, it's going to spiral around this ellipse. So I'll try to sketch this out. It's going to do something like this, and then it'll go back around the other side, and then it's going to come around here, and back around the back side of the ellipse, and then around here like so, and continue along that way. So it's going to spiral around this ellipse. We could call this an elliptical helix.
How do you know it's spiraling now?
If we project the motion onto the xz plane, as t increases, it's going to go around this ellipse. So if we were along the y-axis, if we were looking at it from over here, if we were standing here looking at it, we would see the motion go along this ellipse. But as t increases, the y component increases. It's going to spiral around, and as t increases, it's going to move along the y-axis. So the y, right? So the y component is going to continue to increase. So that's going to move it along the y-axis.
Mr. Beamer?
Yeah.
How do you know which way this ring goes?
Let's see. So what I did, the way I was thinking about it is when t equals 0, we have the y component is 0, and the x component is 0, right?
Yeah.
So then we're going to start at z equals 5, so up here. And then as t increases to pi over 2, the z component is going to be 0, the x component would be 3, and the y component would be some 2 pi or whatever. So then it's going to go down that way. So kind of like we did with parametric equations, just look at what happens as the parameter increases to tell which direction it's going to go. So when we talked about surfaces, so this in the xz plane is an ellipse, but y can be any value. So no matter where we are, we have this ellipse, this elliptical shape for every value of y. So if we think of an ellipse for every value of y, we just move anywhere along the y-axis. So it's like that ellipse is kind of sweeping along the y-axis to give us a cylinder. Oh, there's your passage around. All right. So it can be a little tricky to start thinking about what these curves look like. But what you want to do is apply what we've learned about surfaces and about parametric equations, and apply that to these vector value functions. So this is one example of looking at that. Let's see. I want to ask some true or false questions, and we'll talk about these true or false questions. So the first question. So these are all true or false. So we have f, g, and h are first degree polynomials. And we have the curve given by x equals f of t, y equals g of t, and z is h of t is a line. So we want to decide, is this true or false? So we have these parametric equations. We could think of it as a vector value function. So f, g, and h are first degree polynomials. We want to know whether it's true or not that this curve is going to describe a line. Bull's tentatively nodding yes. Star says yes. Maybe. Anybody else have an idea? Let's look at how we might be able to think of this. So a first degree polynomial. What is a first degree polynomial in the variable t going to look like? How would we write one? See, some ct. So we could say that x, if we're going to write this first degree polynomial, we could say x equals ct, y equals some other linear polynomial in t. So y could be, let's say, d. Let's not use d because that looks like the derivative. Y looks like y is some constant e times t. Or how about c1? Y equals c1t. Z equals c2 times t. Thinking back to when we talked about lines and planes, what are these set of equations describe? Isn't this a line with direction numbers c, c1, and c2? So this is a line parallel to the vector c, c1, c2. So if we write our functions as linear polynomials in t, we end up with a line. So this would be true. Does that make sense how we broke that down? All right, let's look at, now we're going to ask the question slightly differently. Question 2. If the curve given by these parametric equations, x equals f of t, y equals g of t, and z equals h of t is a line, then f of t, g of t, and h of t are first degree polynomials. And we want to say true or false to this. So what do we think on this one? False. We have some definite falses. What would be an example? Sorry? One of them could be a constant. Okay, that would work. Any others? Two of them could be a constant. Any others? All of them are constant? That would just be a point, right? What about something more complicated? What's that? Right.
If f of t and g of t are both x squared, it would just create.
Okay, so that would be good. So we could say f of t equals x squared, and that equals g of t. And what did you say, Levi? Garrett?
Oh, what if they're all
If they're all x squared? So we have x equals y, x equals z, etc., etc. Doesn't that describe a line? Yeah. So this is
The
false.
only thing is I would actually create a v, wouldn't it? Because of the fact that then you're doing negative, it would go back upwards.
Mine is a negative though.
Well, t can be negative in this case.
Well, let's say that instead of x squared, let's say e. How about e to the t?
Yeah.
There we go.
Oh, I can't go negative.
Right. So then we get x equals y equals z, and we have these. This is not linear, but we have a line. So this would be false. All right. I have another one. So my third one is objects. Objects traveling along these curves, R of t. That's an A, and this is an E. Objects traveling along are along these curves, ti plus t squared j. And u, some other curve, equals 2 plus t I plus 8t j will collide. So we want true or false on this. So with these, if objects were traveling along these two curves, would they collide? John says no.
Because in order for them to collide, the x and y, they have to be at the same point at the same time.
Okay.
And so that would mean if the x coordinate is defined by t in the first one and 2 plus t in the second one, t is never going to equal 2 plus t. Does that work?
Yeah. So Sean says they have to be at the same point at the same time. So for that to be true, we need t equal 2 plus t. Can that ever happen?
Oh wait, that happened to
If t equals 0? If it was multiplication, that would work, right? We need t equals 2 plus t. We have to have the x coordinates to be the same at the same time, and this can't happen. So we're going to say this is false. So they might be at the same point, but not at the same time. So this is kind of like what we talked about when we talked about polar graphs, intersections of polar graphs, that they might cross each other, but not necessarily at the same time. All right, last true/false question. If R of t, t squared is t squared I plus t sine tj plus t cosine tk. This is on this curve. On the paraboloid, x equals y squared plus z squared. So what this is asking, like the spiral motions that we talked about, our curve the curve described by the vector valued function was on the cylinder. So we're asking, is this curve described by this vector valued function, does it lie on this paraboloid? So if we, as t increases, is our vector on this paraboloid? So we want to know true or false. Say true. And why are we saying true? What could we do? How could we show that this is true? Okay, so Cole says that's perfect. Cole says t squared equals t sine t squared plus t cosine t squared. And that's exactly this relationship. So this vector value function is going to lie on this paraboloid because the components relate to each other in exactly the way that's described by this surface. So this vector valued function, this vector is the terminal point of that vector is always going to be on this paraboloid x equals y squared plus z squared. So this is true. And I think it's kind of cool that with this compact, easy compact notation that we can describe motion on a kind of a complicated surface. So this motion, if we think of this as t, our parameter being time, and time changing, this vector valued function describes something moving on this paraboloid. I think that's kind of illustrates the power of analyzing curves, analyzing surfaces with vectors. Questions on those?
So how do you set it equal to t squared?
Well, let's see. Cole said that I'm interpreting your thinking here. So when we've worked other examples, when we had a sine t and a cosine t, we think of the Pythagorean identity, sine squared t plus cosine squared t equals 1. So I think what Cole is saying is if we squared this component and squared this component, we would end up with t squared. Yeah, then we just factor out the t squared. The other way, the way that I looked at it, I usually look. I think Cole saw the bigger picture, kind of all at once. I would look at these two and say that normally how I would do it is look at the y and the z component and say that if I did y squared over t squared and that add it to z squared over t squared, that would equal 1. And it's essentially the same thing as we're saying here. All right. The next thing that we want to talk about is if we have some kind of graph, we want to be able to represent it by a vector valued function. So we want to translate from a given graph to a vector valued function. So let's look at an example of doing that. So say we're given, we want to find the vector valued function. And we're going to say not v, but vector find vector valued functions for the boundaries of this region. So here's our region. We'll do a nice one just in the plane. So we're in the XY plane. It should be X, sorry. And our region is going to be, we're going to go along the x-axis here. And we're going to go here, here, and here. Let me back up here a little bit. And my angle here is 45 degrees. And here I'm at x equals 10. And this curve is x squared plus y squared equals 100. So we want to describe the boundaries of this region, the boundary of this region with vector valued functions. So I'm going to break it. What I would normally do with a problem like this, we're going to break it into three pieces. So let's look at three different pieces. So for the first edge of this, for the first part of this boundary, for 1, I think it's going to be easiest just to use rectangular coordinates. So how could we describe this as we're moving from 0, 0 to x equals 10? Excuse me, x equals 10. How can we describe that? Let's think, first off, let's just think of parametric equations. How can we describe that with parametric equations? X equals t? Sure. And y equals 0. And we're going to say t, what does t vary from? 0 to 10. So 0 less than or equal to t, less than or equal to 10. So that would be parametric equations for this curve. So let's turn that into a vector valued function. So r of t for the first boundary is just going to be ti for 0 less than or equal to t less than or equal to 10. So that's just going to take us from here to this point here. For region 2, we're on a circle, so that makes me think let's use polar coordinates. So how could we describe this little piece of the boundary in polar coordinates? R equals 10. Okay. And how would we translate that to some kind of parametric equation with an x and a y? How would we translate that to rectangular coordinates? X squared plus y squared equals 100. So we have that equation. So how are we going to write that as a vector value function? What have we been doing when we have some kind of circular 10? Okay, so x equals 10. What do we want to call it? 10 sine theta. Y equals 10 cosine theta.
What do we want x to be cosine? Well, it doesn't really matter.
I think if we pick x as sine, when I guess would it be easier to pick cosine for x? It just depends on where we start theta. Yeah, we just change the range, right? So if we pick x equals cosine theta, x equals 10 cosine theta, and y equals 10 sine theta. Then we can start theta at 0. And that would just make it a little neat, nicer to write our function. So our vector valued function, r of theta, I guess we're going to use theta. We could write it as t, is going to be 10 cosine theta I plus 10 sine theta j for 0 less than or equal to theta less than or equal to pi over 4. So that's going to take us up to this point. And then for boundary 3, so we're starting up here at this point, and we're moving on this line back down to 0, 0. So what is, if we were going to describe this line in rectangular coordinates, what would that line be in rectangular coordinates? Y equals x. So for 3, y equals x, but we're moving back to the origin. So as t increases, we want our coordinates to get smaller. So what do we need to do here? Well, first off, what point are we starting at here? What would be the rectangular coordinates at this point? 5 square root 2, 5 square root 2. So if we plug in pi over 4, at the end of this, we plug in pi over 4, and we get the point 5 cosines, or 5 square root 2, 5 square root 2. So someone said, so we're starting at 5 square root 2 and we're going back to 0. Change the t. So we could say r of t equals 5 square root 2 minus t I plus 5 square root 2 minus tj. So we have y equals x, and 0 less than or equal to t less than or equal to 5 square root 2. So this will take us from the point 5 square root 2, 5 square root 2. As t increases, it'll take us back to 0, 0. So when we want to describe the boundary of a region with vector value functions, usually you break the boundary into different pieces. You don't have to use the same parameter for each boundary. Just define your vector value functions for each boundary, and define your parameter for each boundary, and that gets you a description of your curve. Are you enjoying the Tranya yet? Not yet?
I'm relishing it.
You're not relishing it?
No, I thought I am.
You are relishing it. Good. All right. Any questions before we move on? So what I'm hoping to accomplish here in these first two lessons about vector valued functions is we're going to be using vector valued functions for a lot of different things over the course of the entire semester. We're kind of dipping our toes into the pool, kind of getting our feet wet a little bit, kind of getting a little taste of working with these vector valued functions, so that when we get to chapter 15 and we dive head first into the pool, we have a little bit of a foundation. We know what to expect a little bit. All right, this is my favorite example of this entire chapter, I think. This next one. We want to sketch the curve represented by the intersection of x squared plus y squared equals 4. And z equals x squared. Then we want to represent the intersection we want to represent the intersection by a vector value function. With the parameter 2 sine t. Or sorry, with x equals 2 sine t. So let's look at the first part. I'm going to draw a set of axes here, and we'll start drawing some pictures of our surfaces. So what is x squared plus y squared? What kind of surface is x squared plus y squared equals 4? Okay, circle in the xy plane. So in 3 dimensions, it's going to be cylinder. And what's going to be our axis? Z-axis. So we have a right circular cylinder about the z-axis, and our radius is going to be 2. So here's my cylinder, my right circular cylinder along the z-axis, a portion of it. So there's a portion of that cylinder. What kind of surface? Good morning. We were talking about you earlier.
Really?
Yeah. We only said nice things. All right. What kind of surface is z equals x squared? A parabola, and we call is it a paraboloid? When we only had two of the 3 coordinates, what kind of surface was it? A trough, and we call those kinds of surfaces cylinder. So it's a parabolic cylinder, and it's going to be along which axis? The y axis. It's along the coordinate that's missing. So I'm going to sketch that one in red. So I'm going to sketch the parabola out here. So there we are behind the YZ plane, and here we are in front of the YZ plane. And my parabola is my cylinder is going to go along the y-axis, and it's going to run into this other right circular cylinder. So when we're thinking of this intersection, we want to think of this right circular cylinder and this parabolic cylinder kind of slicing through the other cylinder. So what it's going to do is our parabolic cylinder is going to hit the right circular cylinder here, and I'm going to try to sketch this intersection in blue. So that's where on the front side of this, on the side of this right circular cylinder that we're seeing, this is how it's going to cut through that cylinder. So down here on the y-axis, their intersection is going to cut through just at a point. So it's just shaving that off and a line.
Why
No,
Okay, so stick with me here, and then on the back side,
Yeah, and I was like, that doesn't.
On just our side.
on the back, so I just sketched on just our side,
I see. Yeah,
I see it.
I see it.
and then on the back side, stick with me, guys.
Yeah, you
Then on the
don't
back
want-
side, we're going to have a shape. It's going to cut through like so,
You can see this part.
and on the back side, it'll cut through like this. So this the parabolic trough cuts through the cylinder on the y-axis down here. It's just going to be right on the line. Up here on the sides is where the side of the parabola is cutting through, and then as it goes through, it's going to be down here and again on the y-axis. So I know this is hard to visualize, so I made a model. So here's our right circular cylinder. The dotted line that I drew here is the XY plane, and it's not a perfect parabola, but it's cutting through the cylinder. So pass that model around.
He drew this part right here. You drew this part.
I drew the curve. Yes, that's on the boundary there. So pass that around and take a look at that.
Because you drew it one side of the parabola, or the other one side of the intersection.
Right. So I drew this front side of the intersection that's on our side of the YZ plane
What's that called?
first. So it's a little hard to visualize, but so I made the model to help us see it.
He doesn't have the top.
So yeah, this shape I'm not sure has a name. It's just the intersection of those two.
It looks like
Kind of a saddle shape. Yeah.
Yeah, that's right.
It's like the edge of a saddle.
Yeah.
It's like the edge of a saddle. That's a good description. All right, and while that model goes around,
we're taking a really weird path around.
while that goes around, let's do our next part of our problem. We want to represent the intersection by our vector valued function. And the problem was nice. It gave us how to represent x. 2 sine t. So if x equals 2 sine t, given this cylinder, what are we gonna let y equal? 2 cosine t. So we have x equals 2 sine t. Y equals 2 cosine t. That will give us this relationship, x squared plus y squared equals 4. And z, what does the other equation tell us? Z equals x squared, so z has to be 4 sine squared t. And now we have our vector valued function. Our t equals 2 sine ti plus 2 cosine tj plus 4 sine squared tk. Now, to me, this is a really awesome thing. As that goes around, or looking at the sketch, that's kind of a complicated curve.
So that vector value function is looking in blue.
Yes. So this vector value function would describe that curve. So the relationship between the x and the y component gives us x squared plus y squared equals 4. And the relationship between the x and the z component gives us z equals x squared. So this vector valued function, as t changes, it's going to be, the x and the y component are going to be on the right circular cylinder, and the z component is going to be on the parabolic cylinder. So it's going to satisfy both of those at the same time. So that's going, and what the intersection is the what satisfies both of those conditions at the same time. So to me, that illustrates the power of vector valued functions. Is we're able to represent this complicated curve relatively easily and compactly with a vector valued function.
I'm surprised with you. I like the number 67 in Parabola, where it's the cone spiral.
Right,
And
right.
it's like, that is such a weird function.
Right, right.
You can do it so easy with vectors. It's like, oh my god.
All right, there's one last little piece of information that I want to talk about. Let's stay focused, guys. We're almost done. One more piece of information that I want to talk about with vector valued functions, and then we're done with section 12.1. So we talked about visualization. We talked about curves representing curves, intersections of surfaces, which I think is a really cool thing to be able to represent this intersection with this vector valued function. I just want to talk really quickly about limits and continuity. So, for most operations with vector valued functions, we can just transfer over the rules, the things that we know about real valued functions, just component by component. So a vector valued function basically is just a real valued function for each component. So the rules that hold for real valued functions generally hold for vector valued functions, just applied on a component by component basis. So we just apply the rules to the x component, the y component, and the z component. So just in terms of limits, if we have R of t is our favorite representation here, f of t I plus g of t j plus h of t k. The limit as t approaches a of R of t, we're just going to apply this limit component by component. So that's just the limit as t approaches a of f of t I plus, and we're going to do the same thing to the next component, the limit as t approaches a of g of t j, and we'll do the same thing to the z component. So this is true as long as the limits of our individual component functions exist. And the limit theorems that we've talked about, all the properties of limits that you're familiar with already from real valued functions, just apply component by component. So we can, if we're looking for a limit, we can just apply the rules that we already know for limits on a component by component basis. The same idea holds for continuity. If we're going to say that R of t is continuous, at t equals a, if, what are our conditions for continuity? So think even more basic. Limit as t approaches a of R of t. What has to be true of the limit for a function to be continuous? If what someone said, the limit has to exist. And okay, so the limit basically from both sides. And what's a more compact way of saying that? the limit as t approaches a of our t has to equal our function value. So that guarantees that the limits, basically the limits from both sides are the same. And the ideas that we've developed, that we've already worked with for continuity, apply component by component. So these are our just our down and dirty rules for limits and continuity of vector value functions. We just apply our rules for limits and for continuity, component by component. Any questions? All right, homework. Yeah. Yes. There probably is a more compact way that I could write that, but I just...
You have to find some really odd algorithm.
Right, so yeah, some kind of even odd thing.